The investigation into ice cream sales isn't over yet. In our last chapter, we cracked the basics. We learned how to make our data behave, got it stationary, and built our first ARIMA model. It worked well, until I noticed something. Remember when I said there's one variable I can't control? The temperature? Well, turns out it's hiding something. When I plotted the temperature data, I saw a pattern, repeating again and again, a repeating crime scene. Now, ARIMA was a good detective for trends and noise, but this is something else. This is seasonality, a rhythm that repeats every few months. So today, I'm upgrading my toolkit. We're moving from ARIMA to SARIMA, Seasonal Autoregressive Integrated Moving Average. SARIMA doesn't just look at what happened yesterday. It remembers what happened the same time last season. It's like a detective with a diary. It keeps notes from last year to solve today's mystery. We'll apply SARIMA on our temperature series, learn how it handles seasonal behavior, and then, oh yes, we'll bring that forecast back into our ice cream sales case. Because this story isn't over, it's just getting cooler. Okay, detectives. First rule of any good investigation: make the evidence steady. In time series world, that means stationarity. The series should have a roughly constant mean and constant variance over time. If it doesn't, our models will get confused. Looking at the temperature plot, I noticed something useful. The variance looks pretty stable. The swings aren't getting wildly bigger or smaller. Great. That means we probably don't need a log transform this time. But there is a problem. There's a clear trend. The line slowly moves up or down over time. And you already know what we do with trend. We remove it so the series behaves. My tool of choice? First-order differencing. Subtract today's value from yesterday's, or vice versa, and the trend usually goes away. So I applied first-order differencing to the temperature series. If you expected that, good job, you're paying attention. If you didn't, no stress. Rewind to the first video and refresh the basics. That's what the series is for, learning step by step. Now that our series is stationary, the next step, as always, is to study the ACF and PACF plots. These help us figure out the possible orders of AR and MA models. We've already done this dance in part 2, so I'm not going to repeat the steps here. But wait, hold on a second. Something feels different this time. Look closely at the ACF plot. The spikes aren't dropping to 0 right away. They're slowly decaying, but that's not all. There's a repeating wave pattern forming. And in the PACF plot, we do see a few significant lags, sure, but the ACF pattern is stopping us from moving forward. Remember, for ACF and PACF to really guide us, they should look like random noise, no clear rhythm or repetition. But here, there is a rhythm, a very suspicious one. It's as if the series is whispering, I remember my past. This slow decay means the series is carrying a memory, and that memory fades gradually over time. Not good news if we want to build a clean model. So what can we do? Well, when things drift like this, we usually try second-order differencing to see if we can remove the leftover pattern. But wait again! Something even more interesting shows up. Look at this. Every 7th lag in the ACF plot is spiking up and down like clockwork. Every 7th point, 7th lag, repeating again and again. That's not coincidence, that's seasonality. You could probably see it in the original temperature plot too, those weekly ups and downs. But as detectives, we don't rely only on our eyes. We confirm our clues with evidence. So here's what this tells us. Our data is showing a repeating pattern every 7 time periods. And how do we handle repeating patterns? With the same trick we used for trends, differencing. Just like first-order differencing removes the general trend, seasonal differencing removes repeating patterns. In simple words, we take the difference between today's value and the value 7 steps back, 1 full season ago. So if our data is daily and this 7-lag season repeats every week, we calculate. And there you go. That's seasonal differencing. With that, we've taken one more step closer to uncovering the full story behind our temperature data and towards the mighty SARIMA model. So far, we've done a good job cleaning up the case. We removed the trend using first-order differencing. Check. We removed the seasonality using seasonal differencing with a period of 7. Check again. But detectives never trust their first clue. We double-check. So to make sure we're moving in the right direction, I plotted the ACF and PACF again, this time using our new differenced series. And look here. That slow decay we saw earlier, it's still kind of there, but those spikes, they're no longer significant. The series looks much more well-behaved now. We could try a period of 14 instead of 7. Maybe our weekly pattern is stretching across 2 weeks. But let me tell you, these trials are always a bit of a hit-and-trial process. I can guide you, but no one can predict the perfect combination. After all, we're predicting the future, not reading it. Anyway, for now, I'll stick with the 7-day seasonal period. It makes sense for our ice cream sales data, and the plots agree, mostly. But remember this, there's still a small, sneaky problem hiding here. I'll reveal that later, so stay sharp. Now, back to our ACF and PACF. Just like before, we'll use them to find our AR and MA orders. Looking at the PACF, I can see that lags 1, 2, 4, 6, 7, and 10 are significant. Those are my possible AR orders. And from the ACF, lags 1, 4, 5, and 7 are significant. These are my possible MA orders. So, our possible ARIMA model combinations would be built from these sets of PQ. But remember, we're not working with a simple ARIMA anymore. We're dealing with SARIMA, the seasonal ARIMA. In SARIMA, we not only model short-term relationships, but also capture the repeating seasonal ones. That means we again look for AR and MA orders, but this time not in simple lags, but in periods. Since we chose a seasonal order of 7, our lags get grouped into periods like this. From our plots, I can see that both seasonal AR and seasonal MA parts show significance in period 1. That gives us our seasonal AR order denoted by capital P equals 1, and seasonal MA order denoted by capital Q equals 1 as well. We already took one seasonal differencing, so capital D equals 1, and our seasonal period S equals 7. So far, everything fits neatly together. Now let's put this into proper notation. The general form of SARIMA is small, P, D, Q, and then seasonal part, capital P, D, Q, and small s. Here P is order of non-seasonal ARD, is number of non-seasonal differences, Q is order of non-seasonal MA, capital P is order of seasonal AR, capital D is number of seasonal differences, capital Q is order of seasonal MA, and S is number of time steps in one season, 7 in our case. So for our data, based on the clues so far, the SARIMA part will become 1117. And like this, we have multiple possible SARIMA models capable to explain our temperature series. Now that our notations are clear, it's time to see how all these suspects, the AR, MA, and seasonal parts, come together to predict the future. Let's break it down slowly. In the AR part, we listen to what the past values of our series have to say. Each lag, yesterday, day before yesterday, and so on, gets a small voice in predicting today. So if phi1 equals 0.6, it means yesterday's sales still have a 60% say in what happens today. But hey, not just the past values, even the past mistakes or surprises, the residuals, can tell us something. If we underpredicted or overpredicted last time, that error itself carries information. So, theta values tell us how much of yesterday's prediction error we are adjusting for today. Now comes the big one, the seasonal component. Our temperature, after all, don't just depend on yesterday or the day before, they depend on what happened a week ago, because that's when the pattern repeats. So these big phi and big theta terms capture what happened last week, both in temperature and in errors. And when all of these detectives, AR, MA, and seasonal, will come together, they form the full SARIMA prediction equation. So, every prediction we make using SARIMA is like a team effort. recent days whisper their clues, past surprises raise their hands, and last week's trends echo from behind. Together, they give us the most logical guess for what's going to happen tomorrow. After running a few quick experiments and asking the senior detectives, AIC and BIC, which story fits the temperature data best, they gave me a clear answer. I won't repeat the whole ritual, we covered it in ARIMA, so here's the result I'm taking to court. And mathematically, these are the coefficients or parameters we will be targeting to find that can best explain the series. Of course, I'm not going to grind through dozens of equations by hand. I've got better things to do, like drink coffee and stare at clues. Instead, I'll let the computer do the math. I'll use maximum likelihood estimation, MLE, to find the best parameter values for our chosen model. In plain language, MLE is a smart judge that tests different parameter values and picks the set that makes the observed temperature data most likely. It's like trying many suspect stories and choosing the one that fits the evidence the best. After fitting with MLE, we'll still play detective, check residuals, run diagnostics, and make sure the model didn't just memorize the past. If it did, we simplify. If it behaves, we forecast. Now, if you carefully look at this equation, something strange shows up. Something I haven't talked about yet. But if your detective eyes are sharp, you might already see it. Yep, those interaction terms. Where do they come from? Let's catch that clue. Our AR part comes from two pieces, the normal AR part and the seasonal AR part. These two are like two mini polynomials. One handles short-term memory, lag 1, the other handles seasonal memory, lag 7, and B is the past days we are looking at. Now let's multiply them, like multiplying two binomials. Notice that last term, b raised to the power 8. This happens because when you multiply b and b raised to the power 7, you add the powers. And that's how the interaction lag 8 appears, the point where short-term memory, lag 1, and seasonal memory, lag 7, overlap. Now let's catch the same clue in the MA part. In the complete equation I introduced, I should have included the errors at lag 9, 10, and 11 as well. I didn't though. I was in a hurry to close the case, then explain every tiny detail. Shouldn't have done that. Anyways, you got the concept loud and clear now, or so I hope. All right, detectives. Time to put the genie back in the bottle. Ah, I see that smirk. You're thinking, that's not possible. Well, it isn't, but you know what I mean. We've played around with transformations, differencing, and seasonal adjustments. Now it's time to bring everything back together and see the real results. We start with our temperature series, the one that drives our ice cream sales mystery. First thought, should we take a log transformation? Look closely. The variance already looks calm, no wild ups and downs. So, no transformation needed. Note this carefully. You never transform a series unless the variance demands it. Don't go fixing what isn't broken. Next, we take the first order difference. This helps remove any trend, giving us a uniform mean. After that, we inspect the ACF and PACF plots. And what do we find? A slow, rhythmic decay in correlations, almost like a heartbeat repeating every few steps. That, my friends, is seasonality waving hello. So, we take a seasonal difference with period 7, because the pattern repeats every 7 observations. We check the plots again, run a few combinations, and then consult our senior detectives, AIC and BIC, to identify the best fit. The verdict? SARIMA 1.14, 1.117. A perfect blend of short-term and seasonal memory. We fit the model and forecast 14 steps ahead. Look at the prediction line. After a few steps, it starts to flatten out. Why? If you've been following the mathematical equations closely, you already know the reason. If not, well, don't rush to the comments yelling, "Why?" Just rewind the video, rewatch it, and save us both a headache. Kidding, LOL. Now comes the magic moment. We've forecasted the differenced series, remember? So we must bring it back to the original scale. Step 1. Add back the seasonal difference. Step 2. Then add back the first order difference. And voila! The forecasted temperature series comes alive, smooth, rhythmic, and full of meaning. The SARIMA model not only spotted the seasonality but learned its rhythm. All right, detectives, let me ask you something. Is there anything we know about the future, any little clue, that might help us improve our predictions here? Think about it. Maybe the day of the week, like Monday or Sunday? Intuitively, the temperature shouldn't care what day it is. It doesn't check calendars, right? But just for a second, let's assume it does. Maybe Mondays are colder and Sundays are warmer. Who knows? If that's true, we'd need to bring that extra information into our model. And that, detectives, is where SARIMAX enters the crime scene. SARIMAX stands for Seasonal Auto-Regressive Integrated Moving Average, with exogenous regressors. Don't get scared by the name. It's literally our SARIMA model, but with one more helpful feature added in: an exogenous variable, or in simple words, an outside clue that influences the main suspect. Mathematically, it's just adding one extra term to the SARIMA equation. And the best part? The maximum likelihood. Estimation we already used will quietly do all the hard work. Estimate this new coefficient beta for us automatically. One more clue, one more coefficient. Easy. Now, if we remove the seasonal part from SARIMAX, what do we get? Yep, ARIMAX. It's just our ARIMA model, but with extra outside information helping it predict better. Let's bring back our original ice cream sales case. We've already forecasted the temperature series using SARIMA, and now we can use that forecasted temperature as an exogenous feature for our ARIMA model. Makes sense, right? Higher temperature, more ice cream sold. But wait, there's more. We can also include day of the week as another clue, because honestly, even if temperature doesn't know it's Sunday, people surely do. And they buy more ice creams when they're free and chilling out. So to summarize, SARIMA helped us forecast the temperature, and ARIMAX will now use that temperature, plus the day of the week, to forecast ice cream sales more effectively. The two cases, temperature and sales, are finally connected. But hey, this isn't the end yet. It's just the start of a grander mystery. All right, detectives, time to return to where we started, forecasting the sales of ice creams. Yum, I know, even saying that makes me want one. Just like in the previous video, we started with our sales series. Then we took a log transformation to calm down the variance, because sometimes data can get a little too dramatic, you know? Next, we applied first-order differencing to make the series stationary, so that the average level of the data doesn't keep wandering away. Now comes the interesting part. We fit an ARIMA model with both AR and MA order of 1, but this time, we gave our model a couple of extra clues: the temperature and the day of the week. Yup, these two exogenous features act like sidekicks, helping our main detective model make smarter predictions. After fitting the model, we forecasted 14 days ahead. Then step by step, we reversed everything we did earlier. First, we removed the differencing effect, then took the inverse of the log transformation. And look at that! The forecasted values now make so much more sense. They follow the real-world logic beautifully, all thanks to those extra clues we added, the exogenous features. And that's it, detectives. Case closed. We've got the sales forecast ready, neat and accurate, and ready to present to our client. Remember, sometimes solving a mystery is all about looking for clues beyond the obvious. That's what exogenous features are. Those little pieces of information that make your model smarter. In the next chapter, we'll meet another technique, Holt-Winter's method. This one doesn't dig too deep into every twist and turn of the series like ARIMA does, but it has its own clever way of capturing trends and seasonality. Every detective has their own style, right? But for today, I'm satisfied and content. We've cracked the case, learned a ton, and I can finally sleep peacefully knowing our forecasts make sense. If you enjoyed this case, hit that subscribe button to join the AlgoStock team, and don't forget to drop a comment below. Tell me what you liked, what confused you, or maybe just say, "Hi, detective." Till next time, stay curious, stay logical, and keep stalking those algorithms.